when x equals 30. Okay, good morning, everyone. How did your homework go? Do you have any questions about related rate before we move on? Your last chance was related rate. Okay, number 36. All right, we do that and then we will move on to chapter 4 today. So let's look at that. So draining a tank. So I will read it. Actually, I'll try to put it here in front of us, read it, and then I will remove that. I guess I can do it like this. Yeah. An inverted conical water tank. So we have a water tank in here with height of 12 feet and a radius of 6. It is drained through a hole in the vertex at a rate of 2 feet cube per centimeter per second. So I read that again. So we have a cone, it's inverted, and there is water inside the cone, and the water is being drained at a rate of 2 feet cube per second. What's the rate of change of the water depth? So as the water is being draining, of course, the depth of the water is changing. And the question is, how fast is the water, the height of the water changing when it is at 3 feet high? Okay, so I will draw the picture again and just think through that. So we have this cone. Okay, and there is water inside the cone. So that's a cone, it's 12 feet in height and it's 6 feet in radius. Okay, and there is water, and the water is draining from here at the rate of, let's see, the water is draining at the rate of 2 feet. So the rate is 2 feet cube per second. Okay. As the water drains, the height is changing, and the question is, how fast is the height changing when the height is 3 feet? All right. So let us really understand what this problem is about. All right, so we have the water here. Okay, that is water. And it's draining at the rate of 2 feet cube per second. So the 2 feet cube per second represent what in the problem? So the water is changing. And let us say, let me draw two pictures. So we have, suppose at some point in time, we have water up to here. After 1 second, we have less water because the water is draining. So it was up to here, the water is down here. Another second, again, the water is draining. So we had water up to here, the water is here. And as it drained, the height from here to here is changing. This is changing. Okay, and the question is, so 1 more second, that's really the picture. The water is really draining. And the question is, this height here, how fast this is changing? Okay. Now, question addressed to you. 2 feet cube per second represent what in the picture? The 2 feet cube per second represent what in the problem? I want an answer from you. So when I say the 2 feet cube, what do you understand by this 2 feet cube? What does it represent in the context? What's changing by 2 feet cube per second? How fast is the water draining? Very good. What do you mean by water draining? Rate of change, this is very good. Rate of change of what? That's the question. Rate of change of what? Of the volume of the water. And that's really important. First, the unit should be, tell us a lot. It's feet cubed. That's a unit of volume. Okay, so the 2 feet cubed per second, it means how much the volume is changing per second. So we have water up to here, and then the water dropped by 2 feet cubed. That's how much the water dropped by. And then a second later, the water dropped by another 2 feet cubed. So that's how fast the volume of the water is changing. And what I want to know is how fast the height or the depth of the water is changing. So that's really the question that we have to work with. Okay. All right. So now, what are my variables? And so we're going to introduce the variable that they are changing, the unknown and the known, and then go after the equation, which is, well, not very hard, but that's usually the hardest part. So question is, what are the variables? What's the two things changing in this problem? Okay, I'm putting braces because I want answers. And then what's the given in this problem? And what's the unknown? Okay, so from reading the problem, what are the variables that we actually are of interest for us? The volume and the height. So we introduce them. So let V of T be the volume. That's what's changing. Volume of water at time T. The volume change, and H of T is the height of the water at time T. Okay, now this is the variable. Now what is given to us? What is the given? What do we know in this problem? We know how fast what is changing. We know how fast the volume is changing. So the rate of change of the volume, how fast is the volume changing, that's given to us. It's 2. Is it -2 or +2, you think, in this problem? So it means the volume of the water. If you sketch the volume with respect to time, it's decreasing, okay? Because we're losing water, it is decreasing. It's decreasing at a constant rate in this problem. So it's decreasing like that. At some point, there is no more water. And it's decreasing by 1 second, by 2 feet every second, by 2 feet every second. So this is volume with respect to time. So this is -2 feet cubed per second. What we need to know is how fast the height is changing. And we know it's going to be a negative number because the height is actually decreasing. And we want to know that when the height is 3 feet. Okay, so that's really done. All right, one question before we start finding the equation. Do you think the height is changing at a constant rate? Do you think the height is changing at a constant rate? Yes or no? Is the height changing by the same number of feet every second? What do you think? Okay, why you tell me no? He's absolutely right. Why? Yeah, absolutely not. You guys are right. So because the first second, so the 2 feet in volume, and the cone is actually changing shape. So the 2 feet in volume here, so suppose change 2 feet. So let us say this is 2 feet. So the height changed by that much. From here to here, the 2 feet are higher because the cone is narrower. So the height is going to decrease by a larger amount because the cone is becoming narrower. So when it decreases by 2 feet from after 1 second, from here to here, then from here to here, the height is going to decrease by a larger amount. Right. So now the relationship, the equation that relate the volume and the height. So now we draw the picture at a specific moment in time. We're not gonna draw many pictures because now we have to find the equation. So the equation between volume and height. Okay. Now I have to draw the picture again at time t. What is the scenario? So at time t, this is my cone. And this is my picture. Okay, from here to here, I have 12. From here to here, I have how much? I have 6. And that's the water. So this is h from here to here. That's the height of the water at time t. So that's the picture for us. What's the relationship between the volume and the height? All right. If anybody was able to figure this problem out. First, what's the relationship the volume of a cone? Let us remind, the volume of a cone is, remember, the cone in general, I mean not in general, the cone, any cone has a radius, it has a height. That's really a cone. And the volume of a cone is 1/3 pi the radius square times the height. So that's the volume in terms of the height and the radius, because it changes with both of them. Okay. So in this picture we have here, at time t, that's the water right here. So at time t, the water is up to here. So that's the water up to here. That's what's happening at time t. And my job is to find the volume of the water at this time, because that's where we are at time t. That's the water here. And I need to find the volume of the water at time t. What's going to be the volume of the water? So at time t, the water is not, the tank is not full. So at time t, okay, the volume is 1/3 pi r squared times h. Very good. This is h, no problem. What is r? R, that's a cone. R from here to here, that's my r. And is r changing with time? Is r changing with time? Is the radius changing with time? As time go by, that's my radius. And my radius is absolutely changing with time. So here at time t, that's height, and that's the radius. So now I have a problem. Why do I have a problem? So at time t, the volume at time t is 1/3 pi the radius at time t times the height at time t. So r is not fixed, r is changing with time. So now we need to differentiate. But when I'm differentiating, I only know dv dt, I know dh dt, I want to find this, but I have r. So to be able to solve the problem, I need to find a relation between the volume and the height. The volume and the height. So to do that, I need to express the radius in terms of the height. Okay, so I repeat, if I want to differentiate, I have 3 things changing: volume, radius, and height. So I know how fast the volume changes. I know I want the height, but I have a rate which is varying also. So to be able to solve this problem, I need basically to express the radius in terms of the height. Now, how can I express the radius in terms of the height? And once we do that, the problem is going to become fairly simple. So how to express the radius in terms of the height? So let's see. We're going to do the following. We're going to use the idea of similar triangle in the following scenario. Imagine you take a cross section, basically you go inside the cone and you cut it straight from the middle. So a vertical cross section. And you're gonna get this triangle. That's the triangle. Okay, this is the 6. It's 6 feet. At time t, this is h, and this is r. Okay, so you go a vertical cross section right inside the middle. You have this triangle, and I'm going to reproduce it right here. The reason I'm going to do it here because I want to find a relationship between the radius and the height. Okay, so we're going to use the idea of similar triangle. What does similar triangle tell me? This is my point here, and this is my point here. So we can give those names A, B, 0, C, D. And then I'm going to set up a similarity. So I'm going to say that the triangle ABO is similar to the triangle CDO. And now I set the similarity. H over 6, H over, this was 12. H over 12, this side over that side is R over 6. Okay, so I would do the same ratio. It means that R is 6 over 12H. R is half H. Okay, so that's a similarity. That's a similarity between the radius and the height. So the radius is always half the height. And that's because the initial radius, intuitively, the initial radius is half the initial height. So the similarity tells me that at some point, the same relationship between radius and height will come. So for every time t, no matter what the time is, the volume is going to be. So now I substitute. The radius is changing with the height. So this is times the height. And everything changes with time. So finally, I make this look a little bit nicer because I want to differentiate, and there is HH. I'm not going to keep this. This is going to give me times 1 over 4 times h squared times h. And now I multiply the h's, so give me 1 over 12 pi h to the power 3. And that's the relationship between them. So it's a little bit of work. The reason is that as time changes, the radius changes. So I need a relationship between the radius and the height because I need to differentiate and I know nothing about the radius. So I'm going to express it in terms of height so I can work with my problem. Now, finally, differentiate with respect to time. Okay, and now I say, okay, the volume is equal to that. But as I said several times, that's not V, that's V of t, and that's not H, that's H of t. So now I differentiate. Derivative of the volume with respect to time equal. That's a constant times the derivative of h cubed, which is 3, h to the power 3, times the derivative of h with respect to time. H squared. So finally, I will get the dv dt equal 3 over 12, which is 1 over 4 pi dh dt and h squared. Now, I found a relationship between the rate. So finally, we're going to use the given to find the unknown. Right. So what's given to us? I know dv dt. I know I want to find how fast the height change when the height is a very specific value is equal to 3. So here, my given dv dt is minus 2. That's given to us. And my unknown are the h dt. That's what I need to find when h is 3. Okay, so now I substitute everything verbatim. So dv dt is minus 2 is 1 over 4 pi times h squared, which is h squared 3 squared, times the h dt. And finally, I figured out how fast is this going. So I solve for the HDT. So I will have the HDT equal minus 8 over 9 pi. So minus, and this is, okay. I lost my calculator. Was anybody able to find it? So I will get an answer, so I'm not going to compute it. Minus 9 over 8 pi feet, because it's height per second. And of the problem. Okay, so it's a little bit trickier, but we did similar triangle before when we did the shadow problem. So now we are a little bit more used to the idea of similar triangle. Okay, any questions about that? Very good. Now, today we're going to start moving, of course, we're moving to the idea of how we apply the derivative. And in this section, we did a little bit of related rate problem, our first application, and now this whole section will be concentrated on that. One of the things we will be using derivative for is to find when a function reaches its maximum and minimum value. So we will use it to figure out when the function increases and decreases. So the derivative is going to really tell me everything I need to know about a function. So today we start section 4.1, maximum and minimum. So section 4.1, maxima and minimum. Right? Maxima and minimum. Okay, maxima and minima. All right. So as you see, I have here a graph of a function. And we're going to ask you some questions about the graph. Okay. All right. Okay. Some points on this graph are actually different from other points. Like here, where the function peaks, so the peak and the valley are actually a little bit different than the other point. And we're going to give them name. We're going to give those name. Let me start with this point. What characterizes this point on this graph? What characterizes it? Anybody? What's special about this point? Anybody see anything special about this point? Maximum point. Yeah, right here, the function reaches its maximum value. So the highest value obtained by the function is obtained at this point. And let me say, I call it the point I. So we're going to say that the function f, I'm going to say the following, that the function f, so that's the graph of a function f of x, we say that the function f has an absolute maximum, so absolute maximum at the point x equal to I. So we're going to say that f has an absolute maximum at x equal to I. And the value of f at I is called the absolute maximum. Okay, so we're going to say that f has an absolute maximum at the point I. So there is an absolute maximum right there. Okay, now, by the same idea, something special happened here at b. And my function b, f, will have an absolute minimum, the smallest value the function gets. So that's at I, the function gets its largest value. At b, it gets its smallest value. So we say that f has an absolute minimum at x equal to b. And f of b is called the absolute minimum. Okay, so these are the first two words of today. Now, there are other points which are not absolute maximum, absolute minimum, but really something happened at those points. At this point here, a little bit particular. At here, the function doesn't have its maximum value, but around here, around it, a little bit around it, the function have its max, not all over, but indeed around this point, the function have almost its a maximum value around this point. So we give this a name and we're gonna call it a local max. A local max. So because it's not the largest, the function doesn't have its largest value at this point, but around this point, that's where the function have its largest value. So we're gonna say that f has a local maximum, f has a local maximum at the point x equal to c. Local. Let me write it clearly. Local maximum at x equal to c. Because again, something happened at this point, but it's not absolute, it's not all over, it's just near this point. That's a local maximum. Another point, of course, is this point. Okay, around this point. So here we're going to say again, we have a local minimum. Okay, so again, we say here that f has a local minimum at x equal to d. Okay, so we're going to have local minimum, local maximum, and so on and so forth. All right. Now, what else? What other important are here? The point A is in a way important. That's an end point. And in this book, because that's relative to the book we're using, x equal to a is not considered a local max. Some book consider x equal to a local max because there is some kind of max. In this book, I do not consider the end point as local. The local only happen inside in my domain. They will never happen at the end point. Absolute max may happen at the end point, but not a local max. So what do I mean by that? So for example, let's consider the following graph. Looks like that. That's my endpoint. And my function kind of wiggle like this, go like that, and let us say stop here. So right here. And this is A, B, I mean, this is 0, this is B, and this is D. And sorry, that's not what I want. My apology. I want this picture. Right there. Okay, so let's see what's happening here. What is the absolute maximum in this picture? The absolute maximum occur at x equal to a in this particular picture. So at the end point, we can have absolute max, but we cannot have local max. Local max are totally confined to the inside of the interval, not at the end point. So this function f has absolute maximum at x equal to a. Okay, and then minimum, absolute minimum here, local max, and nothing at the other endpoint. Now, question number 2 is, as some of you already really wrote to me on the chat, is the following. Where do absolute or local, not absolute, sorry, where do local max and local mean occur? Where do local max and local mean occur? Let me go back to this picture. Okay, the local max, local mean, where do they occur? They occurred right here, where one of you told me where the derivative is 0. They occurred right here. Derivative is 0. They occur right here, where the derivative is 0. And they occurred right here. But here there is no derivative, basically. Derivative doesn't exist because we have one tangent from the left, one tangent from the right. The function has a corner. So where do local max, local mean occur? either when the derivative is 0 or when the derivative does not exist. Okay, so that's where they occur. And for this reason, we're gonna give them a specific name, the point on the graph where the derivative is 0 or the derivative does not exist. We call them a name and we call them the critical point. So we're gonna introduce the notion of critical point. What are the critical point? The critical point are the point when the derivative is 0 or the derivative doesn't exist. Why we care about them? Because that's where this local max, local mean of a function occur. Okay, so we're going to introduce our first definition basically. So the idea is, where do local max and local mean occur? So where do local max / local mean occur? Okay, from the picture we say they occur when. That's where the picture told me. Occur when the derivative is 0 or derivative does not exist. That's really where do they occur. And this is going to motivate the following definition of a critical point. So definition. Okay. A number C or a value C is called a critical point. For F, it's called a critical point. I know value and point confusing, but that's really how everybody defined it. They talk about critical point. It's called a critical point for F if, so a value C is called a critical point if the derivative at C is equal to 0 or the derivative at C do not exist. Okay, so a critical value C is called a critical point if the derivative at C is 0 or the derivative do not exist. Local max and local mean occur at critical point. Local max and local mean occur at the critical point. That's why they are extremely important for us, because that's where my function peaks. That's really where, it peaks, pure and simple. So now how are we going to find the critical point? Okay, because that's what we'll be interested in. To find the critical point, it's simple. We just find the value of C. So to find critical point, we have to do the following. So how do we find them? We find where the derivative is 0. It means we set f prime of x equal to 0 and solve for x. So how we're going to find them. And sometimes the derivative may not exist, and we need to find when the derivative doesn't exist. And we find the value when f prime of x do not exist. Okay, so how do we find the critical point? To find the critical point, we set the derivative equal to 0 and we solve for x. And at the same time, we look at the function and we say, is there a value of x where the derivative doesn't make sense? And also we look for those of them. So let us make have a small example to elaborate this. So let me take the following example. I will take two simple problems. Let f of x equal x squared minus 3x. I want x squared. Yeah, very simple one. So example number 1. Find, and this is on the interval 0 plus infinity. So I'm not only interested on this interval. So find the critical point. Okay. So we take f prime, we set it equal to 0, and we compute. F prime is 2x minus 3. So f prime of x equal to 0 will give me 2x minus 3 equal to 0, x equal to 3/2. Okay, so it means we have a critical point at 3/2, and 3/2 is within my interval, so that's my critical point. So let us see what's happening graphically. It means at 3/2, my derivative is equal to 0. So at 3/2, so at 0, my function is 0. So this is my derivative right there. So my function is going to go like this, and that's where my derivative is equal to 0. Okay, now derivative doesn't exist. We don't have any. The derivative is 2x minus 3. The derivative exists for all x's. So the only critical point, is x equal 3/2. Let's take another example, a little bit more, a bit harder. So let me take the function f of x equal x squared times e to the x. And the question is, find the critical point. I did not give you a domain. It means you have to find a critical point for all values of x. Okay? So let us do that. So we're going to compute f prime and set it equal to 0. Okay, what is f prime? That's a product of two functions. F prime is derivative of x squared, which is 2x, e to the x, plus x squared e to the x. And I'm going to set this equal to 0. Okay, and I have to solve. And I told you several times, the key to solving is factoring. So the term that it's easy to factor here is the ex, xex. I factor it, I will get 2 plus x equal to 0. Okay, so I repeat, to solve, usually we try to factor. So when does this occur? If the product is 0, it means one of the term is 0. So let's give me x equal to 0. Now, ex, this is never 0, because we know how the graph of ex is. Ex is the number raised to a power, it's never 0. So x equal to 0, 2 plus x equal to 0. So this gives me x equal to 0 and x equal minus 2. So now we have two critical points. We use the abbreviation CP for critical point. We have two critical points at x equal to 0 and at x equal minus 2. And now this is really, even though with very little information, we are going to actually kind of sketch the graph with very little. I won't have a great graph, but I have an idea. X equal to 0, so this is my function, x squared ex. X equal to 0, something specific happened. Now the output is 0. So, and we have a horizontal tangent. Means right here, I have a horizontal tangent. So I know the behavior right here. I have another critical point at minus 2. So this is minus 2. Now if x is minus 2, that's the function. It takes the value minus 2 squared e to the minus 2. It means 4 over e squared. So at 2, my function is right here. And I know that I have something very specific. I have a horizontal tangent. So I do have a horizontal tangent right at those 2 points. And now finally the question how the graph looks like. Now, of course, you're going to learn exactly how the graph looks like. So my function is x squared ex. My function always is taking positive value. And it's going to look something like this. Then it's going to deep down, and then it will take off. So here, I know its behavior here. And I know its behavior here. It's actually like almost flat here. And then this is really my function. Okay. All right. So finding critical point is really simple. So finding the derivative. Now, I'm going to ask a question. I'm going to go back to the absolute max a little bit, and then I combine. My question is the following. Does every function have an absolute max and an absolute mean? Okay, so if I take any function, f, so does every function has an absolute, not max, absolute max and absolute mean? Okay, so does every function has an absolute max and absolute mean? And let me basically going to ask you a question. How can I draw a function where the domain, suppose I want the domain to be all the numbers? Okay. How can a function, no, absolutely no. How can a function be so that it has absolute max, but no absolute mean? If the domain or the real number, there is absolute max, there is no absolute mean. Absolute max, no absolute mean. So a function may not have absolute max, and or it can go like this. No absolute max, no absolute mean. So there are a lot of pictures. Now, suppose I ask you the following question. Suppose I want the domain not to be all the numbers. Suppose I want the domain to be 1, closed at 1, open at 2. Okay, I'm very clear. All right. Does the function have to have absolute max, absolute mean? Okay. You can somehow in Word tell me how graph a function that have an absolute mean. So let's graph it. Has absolute mean, no absolute max. Okay, and the domain is 1, 2. Is it easy to draw such a graph? No absolute max, it has absolute mean. And the domain is 1 and 2. Is it easy to draw such a graph? Anybody? Would it be a parabola? How shall I draw it? That's my domain. I want a max. Sorry, I want an absolute mean. I don't want a max. A negative parabola. How can I do? Okay, x minus 1.5. I mean a positive parabola. I'm still struggling. So I want to be nice. I want to be defined because, okay, this is a negative parabola. It's a parabola. I mean, regardless how I draw it, it's a parabola. Okay, I'm going to draw a parabola. I'm going to go like this. And I'm going to go like that. So at 2, since it's open, this is going to be like this. I will follow one of your classmates. This is the picture. All right. The absolute minimum is at 1. Does this function have an absolute maximum? What do you think? Back to you. Is there an absolute max? Is there an absolute max? We have to get that clear. Is there an absolute maximum? It means is there a value in the domain where the function have its largest value? That's what absolute max is. Is there a value in the domain? In the domain, it means between 1 and 2, where the function have its absolute maximum. What can you say? Yes or no? No, because at 2, It's not in the domain. And it's absolutely an open circle at 2. So this function has no absolute max. All right, now let me ask the following question. The domain is 1, 2. Okay. And this is harder. I want absolute mean, no absolute max. But I'm closing my domain. Can anybody think of a scenario where the domain is 1, 2, closed, absolute mean, there is no absolute max? Anybody? Anyone? I know it's hard. Maybe if there is no derivative. Okay, let us create a scenario where there is no derivative. Okay, this is a hard question, and I know that. And I'm gonna show you how it occurs and the only way it occurs. So it's gonna occur, suppose I'm gonna let the function have an absolute max here. So I'm gonna make the function to look like that. Watch what I'm doing. That's my function. Okay, so is there an absolute minimum? Yeah, at 1. Is there an absolute max? Is there an absolute max in this problem? No, because there is an open hole here. There is no absolute max. So what's really caused it, as you realize, if the domain is 1, 2, for the function to have this property, it means no absolute max, I have to break the graph. That's the only way out. And it's mathematically a deep idea. I have to break the graph. So in math, there is the following theorem. If a function on a domain, closed domain, it means something like 1, 2 close. If it is continuous, it means the function keep going, then the function has to has an absolute max and has to has an absolute mean. So if the function is nicely continuous, not this scenario, continuous, then this cannot occur. Then an absolute max has to occur and an absolute mean has to occur. Okay, and the question is how to find it. So that's really my question. So eventually we're going to learn how to find absolute max, absolute mean for any function if they exist, because we know that they cannot exist. But today we're going to take the simpler scenario. So if a function f, so that's a theorem. If f is continuous, means there is no jump in the graph, and on a closed interval, AB, so there are a lot of restrictions. The interval has to be closed, then f has an absolute max and an absolute. Has an absolute max, maximum, and not local. I'm talking about max. I'm talking about absolute, and an absolute minimum. All right. So if the function, if the interval is open like this, no, We may have absolute mean and no absolute max. If the domain is all of R, forget it. We may or may not. If the function is not continuous, we may or may not. If it is continuous, we have to have an absolute max and an absolute mean. Okay, so there are some restrictions on the function to guarantee the existence of both of them. So that's really the situation. So now the question is how to find them. So how to find them? How to find absolute max and absolute mean for a continuous function f on interval AB. On an interval AB. So how to find absolute max and absolute mean for a continuous function on an interval AB. Okay. So we know that they are, the theorem tells that they are, so we should be able to find them. Now, since the time is up, I would have to stop right now. And please make sure you do your homework for tomorrow. And again, I owe you an apology for not grading your exam on time. I mean, I have my own reason, but it's my reason. So I started last night, so I hope to get them done by Friday. They take time with me. So my apology again for not doing them on time. Okay, any questions? Oh yeah, of course they do, because, you know, if I graph them, they have tons of them. Watch. You guys can ask any question you want. So those are trig functions. Here, 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 here. Yeah, tons of them. Now the greatest integer function, no, because the greatest integer function is like a step function. It goes like that, like this. So they are step function. Okay, so there is no critical point. They are very special type of function. But the trig definitely have tons of them. Okay, am I answering your question, Zach? Yeah, okay, any other questions? Okay, I see you tomorrow, guys. Bye.